in here. Okay. All right. So you can see immediately that the t distribution is very similar to the normal distribution. It shares most of the attributes that the z distribution has. It is bell-shaped. It is normally distributed. Okay. It's a little bit flatter than the standard normal probability density curve, but it is also like the z curve. It is asymptotic with respect to the horizontal axis. On the horizontal axis, we have our t values, and of course, areas underneath the student t distribution are still probabilities like they were for the standard normal distribution. Okay. Now, another thing, ladies and gentlemen, since we do not know the population standard deviation, we are going to use as a point estimate, we are going to use the sample standard deviation as a point estimate of the unknown population standard deviation. Okay. Now, just like with the normal probability distribution, where it's a two-parameter model in the sense that the mean basically determines the location of the normal curve, and the standard deviation determines the shape of the normal curve. The student t distribution also is a two-parameter type curve in the sense that the mean determines its location in the plane, and something called the degree of freedom ultimately determines its shape. Okay, whether it's flat, where the data values are basically far dispersed around the mean, or if it's very narrow, where the data values tend to concentrate around the mean. This concept of a degree of freedom, ladies and gentlemen, is a little bit beyond the scope of this elementary course in statistics. So we're basically just going to go with it. You can see that as the degree of freedom of a t distribution increases, what happens is the distribution becomes more narrow, and the data values tend to become more concentrated around the mean. For smaller degrees of freedom values, the curve is more dispersed, flatter, and splayed out more. Okay. So the student t distribution here. All right, the t distribution, like I said, is similar to the standard normal distribution. It's bell-shaped, symmetric about the mean, median, and mode are all zero, like they were for the standard normal distribution. And the curve approaches but never touches the x-axis, meaning that it is asymptotic with respect to the horizontal axis. The variance of the t distribution is larger than the variance for the standard normal distribution. As a result, the curve tends to be a little bit more spread out, a little flatter than the standard normal probability distribution. The t distribution is actually a family of distributions rather than a single distribution. Different sample sizes lead to a t distribution with different degrees of freedom, which results in a slightly different shape for the probability curve there. As the sample size increases, the corresponding t distribution becomes more and more similar to the standard normal distribution. And your degrees of freedom increases. And as your sample size increases, the sample means of the sampling distribution tends to become very concentrated around the mean. And for that reason, the student t distribution curve becomes more pronounced with its amplitude. Okay, less flat, less splayed out. All right. So, all right. Now, here is a basic idea as to what a degree of freedom is here. Degree of freedom, the degrees of freedom are the number of values that are free to vary after a sample statistic has been computed without changing the value of the sample statistic. Okay. For example, suppose that a sample of 5 values is as follows. We have a small sample with 5 data points in it. The sample mean for this sample would be 9. All right, X bar. Now, changing the data values will change the mean. In other words, if I was to change any of these 5 observations, that's going to affect the value of the mean. However, so long as the 5 values add to 45, the sample mean will still be 9. All right. For instance, we could change the first 4 values to any number, perhaps 3, 5, 10, and 11. But ladies and gentlemen, if we change or prescribe certain numeric values for the first 4 observations, then that basically coursers or steamrolls the last observation to taking on a specific value in order for the sum to be 45, all right, in order for the mean to be the same. So for that reason here, our sample size was of size 5. We would say that we have 4 degrees of freedom, 5 minus 1 or 4 degrees of freedom in in enabling our sample mean to be the same, regardless of whether we change the first 4 values of our data set here. Now, we only have 4 degrees of freedom, so only 4 of our observations are free to take on any numeric value. But once you assign the numeric values to the first 4 data values, then the last observation, the 5th observation, okay, is not free to take on any value. It must take on a value specifically in tune with the fact that the sum of these 5 observations has to always be 45 for this particular example, so the mean will not change. Okay, so the bottom line is what we just need to remember is that for building these confidence intervals with the student t-distribution, the number of degrees of freedom is always going to be equal to our sample size minus 1. That'll be the degrees of freedom that we're going to use when trying to find our critical t-values or conducting a t-interval to find the confidence interval. Okay. So the degrees of freedom is always equal to your sample size minus 1. Now, when we construct a confidence interval for the mean, the unknown population mean, using the sample standard deviation instead of the population standard deviation, we have to compute the sample mean in order to compute the sample standard deviation. So obviously we're going to know X bar, okay? And as a result of X bar being necessary to compute this sample standard deviation, the sample mean must stay fixed. So as in the previous example, one of the data values in the sample cannot be freely changed, but depends on the other data values. So again, this is just reemphasizing the fact that our degrees of freedom for a sample of size n, when constructing a confidence interval for an unknown population mean, is always going to be your sample size minus 1. All right. All right, now how are we going to find these critical t-values? Well, back in the old days, before we had this marvelous TI-84 calculator, we had to use a t-table in the appendix of our book to find these critical t-values. And these critical t-values are dependent upon 2 things: your level of significance or your level of confidence, and also is dependent upon the number of degrees of freedom, which depends ultimately on the size of your sample. Okay. But ladies and gentlemen, we don't really have to deal with that anymore, because we have a calculator that can compute these critical t-values for us. Let me show you an example. If I want to build a 95% confidence interval for an unknown population mean, then I want 95% of my sample means of my sampling distribution of all sample means. I want 95% of all these sample means to bunch up around the mean of the t-distribution. Okay. And so therefore we're speaking in terms of an interval again, where I want 95% of these sample means to be in this interval here. And only 5% of your sample means are going to be allocated to the upper and the lower tails equally. So if the middle area here is 0.95, that leaves what area that is divided equally among the tails? It leaves 5%. So 5% divided by 2 is going to be 0.025. 2.5% of the area will be in the lower tail, and alpha divided by 2 suggests that 2.5% of the area will be in the upper tail of the student t distribution. Okay. All right, so how are we going to find these critical t values here? This lower critical t value, t sub alpha, negative t sub alpha over 2, and this upper endpoint critical t value, which is t sub alpha over 2. Well, we have not an inverse norm function for this. We're going to have to use what's called our inverse t function. All right, and the argument list for this inverse t function is going to be the area to the left of the critical t value that we seek, just like it was for the inverse norm function. The area is always to the left. And then we're going to have our degrees of freedom, which is n minus 1. Okay, so let's see if we can find these critical t values, between of which lies 95% of our curve, or 95% of our sample means. So to do that, we're going to bring up our TI calculator here. All right. We're going to go to our distribution mode, second vars, and we're going to go down to the inverse t function. Right? Inverse t. So the inverse norm function finds critical z values. Today, we have to use the inverse t function to find critical t values. Area to the left is going to be what? 0.025. If I want to find this lower tail critical t value. The degrees of freedom is n minus 1. So suppose that we have a sample size of 22. So the degrees of freedom would be 22 minus 1, or 21 degrees of freedom. Now, if your function appears horizontal like this, you just got to make sure you type in the area to the left, always of your critical t value that you want to find, comma, and then you need to type in your degrees of freedom, which is your sample size minus 1. And for the sake of this example, our sample size is assumed to be 22. All right, hit enter. Enter again. And there you go. Your critical t values are going to be positive, negative 2.08. And notice those are the same values that are found in the t table in your appendix of your textbook. By using 95% and using 21 degrees of freedom, right? 2.08. So are we all getting that critical t value on our calculator here?
Can you show me how to get to the invoice t on the calculator, please?
All right. So first of all, we got to go to our distribution mode, second vars key. Did you hit that?
Yes.
Do you see inverse t down here?
On mine, it just gives me inverse norm, and then under inverse norm is TPDF and TCDF.
All right, so it's not giving you inverse t, correct?
Yes,
all right.
that's
All right, so if you don't have the inverse t, then you're not out of luck, okay? Because in your textbook, in your appendix, you have a t table, okay?
okay.
Well, let's see where that's at. We got to find that here. That's very important. Let's see. No good. No good. Hold on. Yeah, T distribution here. Okay, it's appendix A-5. In fact, let's go to that table, okay? Let's go to our textbook here. Because some of your TI-84 calculators, some TI-84 calculators do not have the inverse T function. The silver edition does, but not all of them. And if you don't have it, like I said, all is not lost, Liz. You have a table in your book called a T table. Right? Got to go to our appendix. Appendix is way at the back of your book here. Appendix tables. Appendix A tables. Let's see. Yeah. And we want table A-5. Do you see it? T distribution?
Yes.
That's the one you want. So you bring this up. And now, the confidence interval, you select what? 95% in this case, correct? 95% in this case here. And this is wonderful. This table allows you to build confidence intervals for 80%, 90%, 95%, 98%, and 99%. That's a pretty lucrative number of values there. Your leftmost column is your degree of freedom column. And so you're gonna have to go into the 95% column and follow it down till you run into 21 degrees of freedom. So there you go, 21 degrees of freedom. And your 95% column was what? Right here, do you agree? That's your critical T value.
Thank you.
2.080. So you don't need to have that inverse T function on your calculator. If you don't, no problem. Just use the table in appendix A-5, the T table, to find those critical T values. Now, suppose, well, let's see here. All right. Hold on, I'm trying to get my cursor back. Okay. Suppose that you had a sample that had like a sample size of like 350. Okay. So what value are you going to use for 95% for 350? Well, you would have to linearly interpolate in between 300 and 400. That's a fancy way of saying you got to find the average, right? Right in the middle here. So notice for 300, the critical T value is 1.968. For a sample size 400, critical T value is 1.966. Suppose that your degrees of freedom was like 350. So how would you find the average of these two numbers? You would what? Add them up and then divide by what? Just divide by 2, correct? That's how you could find the critical T value for any sample size whose degree of freedom is like 350, dead center between 300 and 400. What if it was more complicated though? What if you had like a degree of freedom of like 398? Well, then what T value are you going to use? Well, 398 is closer to 400, so you would just use 1.966. Okay. You will see, les amis, that when you build a confidence interval or do hypothesis testing, choosing 1.966 that corresponds to a degree of freedom of 400 as opposed to 398 is not going to make any difference in our conclusion. All right. Now, if Alex gives you a weird problem, I don't think it's going to, but if it does, whereby you have to use this T table and you need like, you know, a critical T value for like 300 and maybe 70 degrees of freedom. Well, what are you going to do with that? Because our table only allows us for 300 degrees of freedom and 400, correct? So what are you going to do if it was 370? Well, by default, round it off to the nearest one. So 370, we'd round off to the 400. We would use the 1.966. If Alex squawks about such a thing and gives you an awkward problem like that and marks your problem wrong, bring that to my attention and I will investigate. And all you gotta do is indicate to me that you don't have the inverse T function on your calculator, all right? And I'll be happy to, I'll give you the point back, okay? Long as it's fairly close. I don't think Alex is going to do that to you. I think it's going to be a nice degree of freedom, like what you see in this column here, like 100 or 95 or 90, or like 75 degrees of freedom. But if there's any issue with regards to that, just bring that to my attention, indicate what problem number it is, and I'll go back and investigate. All right. And if I deem it's close enough what you have, I'll give you the point back. Okay. All right. So keep that in mind. That also goes for the calculator too. If you're ever doing a problem on Alex and you're using like the inverse T function to find critical T values, and just say you're off by a little bit, Alex marks it wrong. Well, again, bring it to my attention. What I like is I like to have the name of the assignment and the questions that you're questioning. And and your name, of course. And of course, I'll go in and take a look at it. And if it's, within reasonable limits and Alex is just complaining about a little, slight round off error or whatever, I would have no problem giving you points back. Okay. But if the answer is way off, then obviously there is an error. Okay. All right. So that is the T table. It hangs out in Appendix A-5 in the back of your textbook. Notice this picture up here is indicating how your T table works. It works for areas to the left of the T value. This should not be a Z here. This should be a T, because this is the T table, not the Z table. But notice the areas are always to the left. That's the way the table is geared. So if you have an area to the right of a critical T value you're trying to find, let's say the area is like 0.05. All right. Well, 0.05 is not the area to the right. So you're going to have to subtract 0.05 from 1 and call it 0.95. That'd be the area to the left. All right. But you're not going to have to worry about it until we get into hypothesis testing. That's what's going on here. This is for building a confidence interval. So you'll know what level of confidence the problem is requiring here. It'll just say, construct a 90% or a 95% or maybe a 98% confidence interval or 99%. Again, I don't think Alex is going to deviate from what we have at our disposal in our table. If they want you to build a 92% confidence interval, then just bring that to my attention, okay? If any Alex problem wants you to do that and you do not have the inverse T function, just bring it to my attention, okay? And I'll take care of it. All right, so that's where it is, the table. But for most of us, I guess I will assume that we do have at our disposal the inverse T function. But when I am choosing questions, ladies and gentlemen, on Alex, I'll make sure to only include confidence levels that are conducive to the values you have at your disposal in your table in Appendix A5. I'll make sure I'll choose like only what you're seeing here. I'm not going to choose, confidence interval that maybe is like 93%. Okay, I'm going to choose one of these run-of-the-mill ones here. Okay, so that way, if you don't have the inverse T function, you'll be fine in using the table. All right, so how do we build these intervals? Well, here they are. As I would notice that they're this formula is very similar to our formula that we used to build confidence intervals for an unknown population mean mu, where the standard deviation of the population was known 2 days ago. But today, the only difference is we see two differences. For one thing, we don't see any critical Z values anymore. We see critical T values. That's because we're using the T distribution for building these types of confidence intervals. We also see a surrogate or an alias for the unknown population standard deviation, or a point estimate of the unknown population standard deviation is the sample standard deviation. 2 days ago, we knew lowercase sigma. We knew the population standard deviation, but today we don't. And so we always use the sample standard deviation in place of the unknown population standard deviation. Notice we're still dividing by the square root of the sample size as 2 days ago. And we also have this concept of n-1 degrees of freedom. You'll need to know that to find your critical t values, either using your inverse t function or using the table in Appendix A-5. All right. And again, ladies and gentlemen, the requirements for this interval to be a valid confidence interval is that our sample needs to be random. The sample size is at least size 30, or the population from whence the sample is chosen is normally distributed, in which case your sampling distribution or your sample means will be, which is distributed according to the t distribution, not the z distribution anymore, will still be normally distributed. All right. Normally, we don't really get into the nitty-gritty of checking these assumptions, okay, or verifying that they're true. Normally, our problems, are designed so that we can basically assume that these requirements are satisfied. Okay, let's move on here. All right, here's an example. Suppose we collect a random sample of 9 Galapagos tortoises, and they had the following life expectancies. You can see that these turtles live to a very ripe age. More than 153-year-old tortoise. Tortoise is a huge turtle. So they have a very long lifespan in general. Now, suppose we want to build a 95% confidence interval for the average lifetime of all of our Galapagos tortoises, which could number in the hundreds of thousands or even millions, okay, by using this sample result. Well, first of all, we're going to need the sample mean, X bar, and that's computed by taking the average of all these observations, adding them up, dividing by the number. And ladies and gentlemen, we're going to need to know the sample standard deviation, because we do not know the population standard deviation life expectancy for these turtles here. I got a question. How could we, using our TI-84 calculator, find the mean and the standard deviation of the sample very quickly? We would put the data into a list, and we would use what function? Anybody? What function do we use once we have data into a list?
One var stat.
Find the descriptive statistics. What is that?
One var stat.
Yeah, the one var stats function. All right. So, this is not going to be a big deal. All I got to do is type the values into a list and use one var stats. It'll come back with X bar and your sample standard deviation. Make sure you use S sub X and not lowercase sigma sub X, because this is a sample standard deviation. Next, we need to know our degrees of freedom, and it's always equal to your sample size minus 1 for the purposes of these confidence intervals. Sample size is 9, so we have 9 minus 1 or 8 degrees of freedom. Then, ladies and gentlemen, you can either use your table, the appendix, table A5, or you can use your inverse t function to find your critical t values for a 95% confidence interval. And that critical t value would be 2.306. So again, whether you use your inverse t function to find this, or the table in your appendix, the t table, you should have 2.306. All right, now we can build our confidence interval. We know the mean of the sample is 122.9 years is the average lifespan of these 9 tortoises that were randomly sampled. The critical t value is 2.306 from either a table or our calculator. By the way, does our calculator give us a value that's comparable or very, very close to what the table gives us? We better check on that quickly. We better see if there's any major discrepancy here. So we have how many degrees of freedom? And this is a 95% confidence interval, which means there's 5% equally allocated to the lower and upper tail, which means the area to the left of our lower endpoint critical t value will be 5% divided by 2, which is 2.5%. We have 8 degrees of freedom. And we do get 2.306, same as what the table gives us. That's comforting to know so that we're all on the same page. All right, so there you go. You put the values in here. Notice we're using the sample standard deviation to compute our estimated standard error of our sampling distribution of all sample means of samples of size 9 that were extracted from the parent population. So we're using 34.9 as a point estimate of the unknown population standard deviation. And when you dial up these endpoints of this interval, you'll discover, therefore, that the unknown population mean life expectancy for all of these turtles in the Galapagos, the entire population, which could number in the hundreds of thousands or even millions, should be between about 96.1 years and 149.7 years. Wow, that's a ripe old age, isn't it, for those turtles there? So I guess if we want to live long, we have to start eating food that what Galapagos tortoises eat, correct? I'm not sure what they eat. Maybe you could look that up, but all right. So we're therefore 95% confident that the actual population mean lifetime for all these turtles lies between 96 years and 149.7 years. Okay, that's your 95% confidence interval. Any questions how we built it manually? All right, so that's how you build your T interval manually. How would we build this interval using our calculator? Well, just like 2 days ago, we had a wonderful function called a Z interval function. Well, today, Liz Almond, we are equally lucky in the sense that we have not a Z interval, but if we go to stat tests, we have a T interval function. That's the function you want to use always to build a confidence interval for an unknown population mean when your population standard deviation is unknown. When it's unknown. If it's known, then you use the Z interval. Okay, today we're using the T interval. Hit enter to select it. Notice we have our raw statistics computed for the sample, so we don't select data. The sample mean lifetime was what? Was 122.9 years. Sample standard deviation was was 34.9 years. The sample size was what? 9 tortoises were randomly surveyed. I have a question. How do you think they determine these lifetimes of these tortoises? I mean, think about it. If you're polling, the tortoise that had a lifespan of 149 years, I got a question. Are you going to be around to see how long that tortoise lives? That's so not happening. Do you agree? So how do you think they got this data here, Rizzo? This is a good question. How did they collect this data? Look at these lifetimes. How do you think they may have done it? Anybody? I mean, we're not going to wait around for some of these tortoises to die. We would be long gone before them, correct? So how do you think they maybe did this here? What they could have done is they could have handed off this data to what? A younger person in the department. Do you agree? And they could have handed off the data to a younger person that, latches onto the job. And then they could keep track with different generations. You know what I'm saying? That'd be a way of doing it. But if you think I'm going to stick around and wait for 149 years for a tortoise to, kick the bucket, that's so not happening because that tortoise is going to watch me check out before it checks out. So this is an interesting data set when you think about it. And you can't ask the tortoise how long you're going to live, you know, like they're going to be able to predict their lifespan. That's not happening. All right, anyways, we want a 95% level of confidence here. And we can calculate this interval here, Liz Ellen. So hit enter. We're going to construct a T interval here. And there it is. From 96.073, which to the 10th place rounds up to 96.1, to 149.7 years would be the 95% T confidence interval for these lifespans. Okay. So do we understand how we built that confidence interval using our T interval function in our calculator? All right, so what's the difference between Z interval and T interval functions in our calculator? What's the difference? They both build confidence intervals. What's the difference? How do we know which one to use? Or does it matter?
If we have the standard deviation, we use Z.
Yep. If we know the population standard deviation, we use the Z interval. If we don't know the population standard deviation, we use the T interval. Good. All righty. Okay. And all of our calculators do have the T interval function. I believe they do, regardless of which 84 model you have in particular. I think we're good in that department, which is a good thing. And this is basically just reemphasizing the fact, ladies and gentlemen, whether you do or do not know the population standard deviation, that's going to dictate, you know, what kind of critical values you and probability distribution you're going to be using in order to ultimately build your confidence interval here. Okay. Now, if the standard deviation of our population is known, of course, we use the Z critical values. As long as the sample size is at least 30, or the population from whence the samples are chosen is normally distributed. On the other hand, if the population standard deviation is unknown, we have to compute T critical values. As long as the sample size is at least size 30, or the population is normally distributed. All right. Regardless of whether or not we know the population standard deviation, we cannot construct a confidence interval if the population is not normally distributed and the sample size is less than 30. So if our population is plagued with outliers and is highly skewed either to the right or left, and we choose a sample, okay, whose size is less than 30, ladies and gentlemen, we cannot use either the Z interval formula we seen 2 days ago, or today the T interval formula to build confidence intervals for an unknown population mean. In that case, you would have to use another technique, which is called a non-parametric way of building such a confidence interval. Or maybe you could go back to the sample and maybe ramp up some more what observations. Do you agree? So the idea here is whether we do or do not know the population standard deviation is going to dictate whether we conduct a Z interval or a T interval. This is just showing your calculator how to access the T interval function and how to populate its required argument list. Notice if we have a raw data set of sample observations, we would have selected the data feature instead of the stats feature. Okay. All right, ladies and gentlemen, let's see if we can maybe go to our textbook and try a couple problems here. Now, today we're doing section 7.3. Entitled Confidence Intervals for the Mean when the standard deviation of the population is unknown. 2 days ago, it was known. Right? Okay, a lot of this we've already we're exposed to it in our PowerPoint here. All right, here's an interesting problem. Let's just look at this example here. In the data represent a random sample of the number of home fires started by candles for the past several years. Data are from the National Fire Protection Association. Find the 99% confidence interval for the mean number of home fires started by candles each year. All right. So 1 year, 5,460 home fires were as a result of candles. Another year, 5,900 home fires were attributed to candles, et cetera, et cetera. So do we understand what these numbers represent here? That's hard to believe that many fires are started by candles, but there you go. I mean, that's crazy. All right. Now, we want to build a 99% confidence interval. So if you want to do this manually, you're going to need the mean of this sample and also its standard deviation. You can throw the data into a list and use your 1-var stats function to find the mean of the sample, which would be about 7,041.4. That's X bar. And then the sample standard deviation could also be determined as 1,610.3 homes. Okay. All right, since we're building a 99% confidence interval, what would be our critical T value? Well, the critical T value, again, is going to depend upon, I mean, how you get your critical T value is going to depend upon whether you have the inverse T function on the calculator or you don't, or you might have to use the T table in the back of your textbook here. Okay, now, suppose you have your calculator and you do have the inverse T function available. Then what you will do is you'll bring it up. And you'll go to stat. T interval. All right, you select stats. The sample mean would be what? They gave us a sample mean was, what was the sample mean? Oh, 7,041. 7,041.4. The sample standard deviation is 1,610.3. The sample size was 7. The confidence level is 99%, 0.99. And we're ready to compute this confidence interval. That's all you got to do is populate your fields. And there's your confidence interval. So we are 99% confident that the mean number of home fires started by candles during a given year is between 4,784.9 homes and 9,297.9 homes. Okay. So that would be your 99% confidence interval there for the unknown population mean of home fires that are started by candles on an annual basis. Okay. Now that's how you do the problem if you have, you know, if you don't have your inverse T function, or you know, you don't even have your table at your disposal. Just use the T interval function. If you want to do the problem manually to find these critical T values, again, on your calculator, if you have the inverse T function, you go to distribution. Oops, hold on. Go to your distribution mode, second bars, go down and grab the inverse T function. And it's a 99% confidence interval. That leaves 1% of the area allocated to the lower and upper tail equally. So what's 1%? 0.01 divided by 2. That'd be 0.005, correct? Degrees of freedom would be 7 minus 1 or 6 degrees of freedom. And there you go. There's no -3. So what is our critical T value here? You can see that it's -3.707 or positive 3.707. Okay, those are critical T values. All right, but what if you don't have that? What if you got to use the table? Well, first of all, let me use my snipping tool here. Because I got to go to a different page in this book here. So, all right. Now, remember, how many degrees of freedom are there going to be? There's going to be 6 degrees of freedom, and it's a 99% confidence interval. Let's go back to our table, way back in the appendix. And it's table A-5. Notice we're going to be underneath the 99% confidence column, the last column. And we got to go down to, how many degrees of freedom was it? It was 6? 6, I believe. So 6 degrees of freedom for 99%. And ladies and gentlemen, there you go. There's your critical T value, 3.707. For 99% confident, for 6 degrees of freedom. Everybody see that there? So if you don't have the inverse T function, don't worry about it. I mean, you do have the T distribution at your disposal to find those critical T values. So either way works. Okay, let's go back to our section here. Well, I don't need this here. Let me get rid of it here. All right, so chapter 7, section 3. All right, let's go down and see if we can do a couple of problems here. All right, so for classwork number 1, I would like you to do problem number 5 here in your textbook. A random survey of 24 couples who had children graduating from high school found that they spent an average of $98.52 in graduation gifts. Standard deviation of the sample is understood to be $5.60. Find a 95% confidence interval for the mean amount of money all couples in the entire population, which could number well into thousands. We want to find the mean amount of money all couples spent for graduation gifts here. So build a 95% confidence interval for the unknown population mean. Go ahead, ladies and gentlemen, and do that problem. That'll be called classwork number 1. Okay. All right, so what we got here is we can use the t-interval function to build this confidence interval. We select stats. The mean of the sample of size 24 was $98.52. Standard deviation of the sample was $5.60. Sample size of 24 and the level of confidence is 95%, 0.95. Go down to calculate, hit enter. And there's your 95% confidence interval. So we are 95% confident. That's saying the average amount that all parents in the entire population spent on their graduating child was between $96.16 and $100.88. Okay, and we're 95% confident in saying that. Did anybody get that confidence interval there using the t-interval function? Anybody at all?
Yep.
Okay. Now that's for building a confidence interval manually. Ladies and gentlemen, there may be some questions like on Alex where they want you to or force you to build a confidence interval, manually, where you don't use the t-interval function, where you're going to have to find your critical t value either using your inverse t function or your table in the back of your book, your t table. And then you're going to have to compute the margin of error and then add or subtract it from your sample mean to basically determine the endpoints of your confidence interval. So because of that, I would like you to know how to do these problems both in a manual way and a non-manual way here. So problem number 6 in our textbook, what I would like you to do is do that one. But I want you to do this problem manually. I want you to show me, how you're actually building the confidence intervals by finding your margin of error. Of course, you need to know your critical t values, the 99% level of confidence. Is one of the nice levels of confidence for your t table in Appendix A5 if you don't have the inverse t function. So let's do problem number 6 manually. Okay, we'll call this classwork number 2 manually. All right. So problem number 6 here. They want us to, it says a survey of 15 randomly selected employed people in Washington, D.C. found that the mean monthly income was $5,050. Standard deviation for the sample is $843. Find the 99% confidence interval for the mean monthly income of workers in the Washington, D.C. area. All right, so our sample size is 15. Therefore, we're going to have 15 minus 1 or 14 degrees of freedom. Sample mean is $5,050 and the sample standard deviation is $843. Now 1 minus alpha is 0.99, since when they want us to build a 99% confidence interval, it means alpha is 0.01, which means 1% is equally allocated for the lower and upper tails of the student t distribution. So 0.01 divided by 2 is 0.005. So now we got to find the critical t values. You can use your inverse t function if you have it on your calculator. Type in the area, 0.005. Comma, degrees of freedom is 14, and that should give you 2.98 for your critical t value. Or you can look in back of your textbook in table A-5. Make sure you're looking underneath the 99% confidence column, and you use 14 degrees of freedom. That should give you the same critical t value of 2.98. And let me just check that real quickly if I could. 14 degrees of freedom, 99%, 2.977. That would be 2.98 rounded off to the hundredths place. Same value. Okay, so that looks good. This is how we're going to build our confidence interval manually. So we put our sample mean in for X bar. This is the critical t value. And then we got our standard error here. Sample standard deviation divided by the square root of the sample size. This is your margin of error. And your margin of error cranks out to give you about $648.63. That's your margin of error. So to find the lower end point of this 99% confidence interval, you take the sample mean, subtract off the margin of error. And to find the upper end point, you take the sample mean and you add the margin of error. This, ladies and gentlemen, would be your 99% confidence interval for the average income of all employees in the area of the Washington, D.C. district. Okay. And we're 99% certain to say that the average monthly employment, average monthly income would be in between these values here. Okay. All right. Or it could actually be an endpoint value. Did anybody compute that correctly manually like that?
Yes.
And I'm curious to see how close this is to a calculator solution. So what I'm going to do is take this problem to the TI-84 and the t interval function. I just want to see, you know, are we close? Are we way off or what? What's going on here? So you would suspect it would have to be very, very close, if not the same. So we go to stat tests, stats. And what was our sample mean? It was 50-50. Standard deviation, sample standard deviation is 843 as we use that as a point estimate for the unknown population standard deviation. Sample size was 15.99, 99% level of confidence. And there we go. Let's crank it out here. And we get this. Comparing it to what we got, it's pretty darn close. You know, we got 4401.37. They got 4402.1. Upper end point, we got manually 5698.63. They got 5697.9. So it's very close. It's very comparable. And again, ladies and gentlemen, if you're doing a problem on Alex and, you know, you type in your answer and Alex comes back and says it's wrong. If it's just a matter of a little bit of round off, you know, I can easily, you know, go in and give you the credit back. You just got to let me know what assignment it is, the problem number, and your name, so I can expedite my correction. Okay. So just let me know if it comes down to a round off glitch. Because there are slight discrepancies, as we can see, between the TI-84 versus the table, maybe the T table, right? Okay, there's slight differences, all right? If that becomes a problem, if Alex does not accept your answer because of a slight round-off difference, please bring it to my attention so you can get your points back. Now, if it's way off, you know, or significantly off, obviously there's a mistake somewhere, okay? And it's a legitimate reason why Alex marked it wrong. But if it's just a matter of round off here, all right, please bring that to my attention. Okay. Now, so far, we've been given the sample statistics. We have not had like a raw data set to work with. I want you to do for classwork number 3, we can call this classwork 3, number 8. And I want you to do this problem both ways. I mean, I want you to, you know, build a confidence interval using your T interval function. And I also want you to build this confidence interval manually. Notice they give us a small sample here, the raw data of a small sample. And they want us to build a 90% confidence interval for the true population mean gas tax. Okay. For all states, right? This sample only constitutes 12 states. So go ahead, ladies and gentlemen, and do this problem both manually and using your calculator. All right. And hopefully our 2 answers are within, you know, within very close limits to each other. Just maybe a slight difference, a little bit of round off. Okay. But go ahead and do that problem. Call that classwork 3. Manually and using your T interval function. I would recommend rounding off your results to at least about the hundredths place, 2 decimal places. Let's just do that. All right, for problem number 8 here. I put the data into a list. I think it was list 1, and I used my 1-bar stats function to find the sample mean and the standard deviation. And my sample size is 12. Degrees of freedom will be 12 minus 1 or 11. 90% level of confidence suggests that we will have 10% of the area of the standard normal student T curve allocated for the upper and lower tails. Divide that by 2, you got 5% in the lower and upper tail. Finding the critical T values in your inverse T function, we type in the area to the left of the lower endpoint critical T value, which is 0.05. Degrees of freedom, you get 1.80. You should also get this value from your table, A5. Building our confidence interval now using our formula. Sample mean drops in here, the critical T value drops in here. The standard deviation of your sample drops in here, and the sample size drops in here. Our margin of error turns out to be about 4.8 cents. These figures are in terms of cents here for the gas tax. So if you take the mean and subtract off the margin of error, you get the lower endpoint of your 90% confidence interval. And if you add the margin of error to your sample mean, you get the upper endpoint. That would be your 90% confidence interval for the mean gas tax for all states. Okay. Did anybody get something like that?
Yep.
Now, we can compare that with the T interval way of doing the problem on the calculator. And you can see that we did get something that's very comparable, very close. 38 point, instead of 38.69, we get 38.7 for the lower end point. It's essentially the same thing, rounded off to tens place. The upper end point is 48.29 manually, 48.284 using the T interval function, which is very close to 48.29. So you can see that there's some, just some subtle discrepancies with the round off. And like I said, just let me know if Alex squawks about such a thing there. Okay. There was another question with regards to this here. It says, does our confidence interval contain the national average of 44.7 cents? So does 44.7 cents lie in this interval? The answer is yes, it does. Okay. And so our 90% confidence interval basically has corralled the actual population average gas tax. It does lie in there, in that interval. All right. Okay. One more problem. Let's see here. Number 12. Now you can build this confidence interval using your T interval function on your calculator. You do not have to do this one manually. And then when you get done, make sure you answer the question that they're asking. Okay. So we'll call this the last classwork problem here for today. Okay, involving thunderstorm speeds. It says a meteorologist who sampled 13 randomly selected thunderstorms found that the average speed at which they travel across a certain state was 15 miles per hour. Standard deviation of the sample is 1.7 miles per hour. Find a 99% confidence interval of the average in which all thunderstorms would move across the state. Now, in finding this 99% confidence interval for the average speed of all thunderstorms that cross the state, we're assuming that it's the same time of the year. Because if you compare the speed with which thunderstorms move across the state in the summertime versus the wintertime, if it's in a southern location, so you even get thunderstorms in the wintertime, you'll discover that on average they move a lot faster during the wintertime than they do in the summertime. So meteorologically speaking, the key assumption is that, we're talking about the same time of the year for all states here. Okay. All right, now the question is this: if a meteorologist wanted to use the highest speed to predict the times it would take the storms to travel across the state in order to issue a timely warning, what figure would she likely have to use? All right, so go ahead and build that confidence interval using your T interval function and just answer the question. That's the last classwork, number 12. Okay, so using our T interval function for this problem number 12. We use our stats, sample mean speed was 15 miles per hour, standard deviation speed 1.7 miles per hour. 13 thunderstorms are randomly surveyed. We're building a 99% confidence interval for the mean speed at all thunderstorms for this particular location and time of the year would cross the state. The speeds was what they would cross the state. We just build this 99% confidence interval here. And we do get this right here. Now, if this meteorologist wanted to use the maximum speed, that thunderstorms cross the state, what value would they choose in this interval? What do you think? What speed would they choose if they want to err on the side of the maximum potential speed these thunderstorms will move across the state?
16.44.
Yep, the upper end point, 16.44. And that probably would be a wise figure to use for safety reasons. Because if you choose 13.56, when in fact your storm is racing across the state, that would be a bigger error, correct? And it could mean a difference between life and death in certain situations. If the storm is packing a tornado. So it's wise to know this stuff, right? Now, the last problem we had a raw data set, and I forgot to mention that when you build a confidence interval for a raw data set using your T interval function, if you have raw data in your list, I don't know if I still got that data in there. I'm going to see. Yeah, I do right here. Okay. If you got raw data in a list and you're trying to build a T interval, then it's a simple matter of selecting not stats, but selecting data. And make sure your data is in the proper list. List 1. Leave frequency is 1. Confidence level is 99%. Calculate. And it's that simple. If you have your data in a list. Okay. And there you go. All right. So today we looked at how to construct confidence intervals for an unknown population mean where the population standard deviation was unknown. In such a case, we had to use the T distribution to generate the critical T values, to generate our margin of error, to generate our endpoints of our confidence interval, or to build the interval, using the calculator directly, we had to use the T interval function as opposed to the Z interval function that we used 2 days ago, where it was assumed that the standard deviation of the population was known. All right, so I will update the homework on Alex, get that up and running. And if there's any other questions, I'll be on the line for the next couple of minutes. If you don't have any questions, have a great weekend.